Thank you very much, and I think it's wonderful to be here. As you guys can see that I was very eager to put my Hawaiian shirt on. So today, before I give my presentation, I would like to acknowledge a couple of folks that have contributed to this presentation. First is my PhD student, Te. So today, what I'm presenting is actually his PhD dissertation. He's going to defend it next year. And also my colleague, Peng. Peng is an early adopter of machine learning in water resources. And now I would like to focus your attention on the left slide. This is the Colorado Front Range. It covers an area of about 3,400 square kilometers. In 2013, we have a rainstorm event that triggered more than 1,100 debris flows. So we figure that in one single event trigger a large number of debris flows. So this would be an excellent test bed for us to test our physics-based model, to test the machine learning model, and then to see if we could use a physics knowledge to improve our machine learning model's performance. So the figure on the right actually is a machine learning model's prediction of debris flow hazards. The red color indicates a high risk. The blue color indicates low risk. Now the ground truth are the red circles. They are the debris flow actually mapped. So the machine learning model does a very good job already. So the key is how do we incorporate landslide physics into machine learning models to improve their prediction even more. So I want to give an overview of physics-based and machine learning models, and I will jump into the data set, which is the debris flow inventory and some of our input parameters. And I will focus on the performance of three models. The first one is a physics-based model, machine learning model, and the physics-guided machine learning models. And I will make some conclusions. So if we compare if we compare the use of data and the use of theory, then we have different camps. So for machine learning folks, they think they use a lot of data, and some of them, they even have an opinion that we don't care about the physics. As long as we have sufficient amount of data, machine learning can figure out the mechanism behind it. So they can do a good job covering large area, but the problem is when they transfer their learning into a different area, then they have some trouble. Now we have also on the other camp, we have some geotechnical engineering folks, traditional folks like me. We heavily use the physics knowledge, right? Because we have received the training. And then we use the site-specific data, which is a small amount of data, and we can do a really good job. I like to borrow David Frost's phrase that we like to chase soil particles. We fully understand the soil behavior, so we don't have to use that much data. But then the problem is our result is very site-specific. So we could have a happy medium, that is we use a physics-guided machine learning model. So we incorporate the physics into the machine learning model so that our result will be much more generalizable. So what our model gained in one area can be transferred to the other area. And we can also improve physics consistency, and we can interpret our model a lot better because machine learning models are viewed as a black box in our community. So let's take a look at the data set. So in this Colorado Front Range, it covers a large area. Now we're only going to focus on the Boulder County, which has about 791 debris flows. So most of the debris flows occur in this Boulder County. So that's our study area. Now let's take a look at data set. Now we know that debris flows or landslides in general, they are caused by a combination of soil conditions, hydrologic conditions, and slope conditions. So here I have identified line contributing factors. Now we select these line factors also because we have publicly available data for us to use. The first one, we have a first group is elevation, slope, aspect angle, and the topographic wetness index. We can get this from three-dimensional digital elevation map. So USGS has this information. The resolution is at 10 meters. The next one is the normalized difference vegetation index, NDVI. The reason we want to use this is vegetation index has something to do with the soil apparent cohesion due to the vegetation roots. So we have a Landside satellite information will provide that. And the resolution is 30 meters. Now we also have a sand content, clay content, bulk density, and the field capacity. So these are, we can have an open land map, we already have this information. And the open land map is already embedded on the Google Earth engine. So the resolution for this is 280 meters. So now this slide shows the visualization of all the line contributing factors in our study area using a contour for each factor. So now let's take a look at the physics-based model prediction. So we are going to pick the simplest model, which is the infinite slope model for shallow debris flow. So we can make an assumption because it's a heavy rainfall. So we assume that all the surface material is fully saturated. We also have a parallel seepage problem. Then we have this well-known equation to calculate the factor of safety. And then we also have these 6 parameters. Now we know the statute unit weight we can already get from bulk density, that is what we already know. And the unit weight of water is already known. And the slope angle is already one of the line contributing factors. So we only need to figure out the cohesion, friction angle, and the sliding layer thickness. Now it turns out that for friction angle, we can use the sand and the clay content based on Carlos and Marina's work in 2017. For cohesion, we make one very simple assumption. We think it is proportional to the NDVI to present cohesion from surface vegetation. Now for sliding layer thickness, that is difficult to obtain, but we're also going to make a very simple assumption. So essentially imagine we can do a post-disaster survey. We figure out in this area, what is the thickness, the sliding layer thickness. That is our H max. We also know our thinness, the sliding layer thickness, which is H minimum. And then we also know what is the highest elevation in our study area, what is the lowest elevation in our study area. Then we can just make assumption that the sliding layer thickness is inversely related to the elevation. As the elevation goes higher, the soil cover becomes smaller, so the sliding layer thickness will decrease. So this is the simplest equation we can come up with. So let's take a look at now we can calculate the factor of safety for this and evaluate the debris flow risk. So this is our debris flow susceptibility map for the study area using our simple infinite slope model. Now, so again, the red color is essentially the contour is the factor of safety. So the debris flow, actual debris flows are these black triangles. So clearly, the simple model can really map this debris flow risk in this area. We have AUC score of 0.903. In this presentation, I try not to use any machine learning jargons, but AUC is something I have to use. Essentially, this is a binary classification problem. So either you have a debris flow or you don't. Either it's 0 or 1. So for a perfect binary classifier, AUC score would be 1. That means at every single point, you get it right. And then for a random classifier, you get an AUC score of 0.5. You have 50% chance of getting it right. So we have this simple model, we get AUC score of 0.9. That's amazing because we did not do anything extra. So my student showed me this work. I thought this is good work. I'm really impressed. And then he wanted to manipulate these equations more to get a higher AUC score. I said, no. If you manipulate this more, then you are cheating because you are not doing blind predictions. So we're happy with this. So let's proceed. So now let's take a look at our machine learning model's performance. So in machine learning, essentially we have input and output. So the input is essentially the line input parameters we just discussed. The output is essentially you have a failure or non-failure. So in this study area, we have 791 debris flow locations, and we also have to have a balanced database, we also randomly sampled 791 long debris flow locations. So we have a 50-50 debris flow versus long debris flow. We have a balanced information. Now we use this to train our model. So essentially we use a 5-fold cross validation. We divide our database into 5 folds. We use 4 folds to train the model and use the remaining fold to test the model. And we repeat this 5 times so that every fold is used once. And then the average performance is our model performance. And we have tested the various of machine learning algorithms. So here I want to show you the random forest and the gradient boost machine. So these two models that are bracketed in this red box. So you have an AUC score of 0.947. This is amazing, and this is the map. When my students showed me this result, actually I was very depressed. I thought the machine learning did not rely on any physics and predicted 0.947. That is much better than our physics-based model. After 20 years of training, I figured that I might be out of a job pretty soon. So I said, the geotechnical engineer inside of me said, let's see if we can do better, how to incorporate the landslide physics we know into machine learning models. So there are many, many ways to do this. So today I just want to show two very simple ways to accomplish this. The first one is so-called the physics-guided model initiation. So in many machine learning models, you have these parameters that need to be initialized, and then they get optimized during the model training. So here I use this two-layer of ANN, artificial neural network. That's the simplest one. So we have these weights for each layer. So these weights need to be initialized properly. So now in traditional machine learning model, we initialize them with random variables. They follow certain statistical distribution. Now, if you don't have enough data to train your model, then your model may not, the machine learning may not be able to optimize this enough so that you have a good performance. Now, in physics-guided machine learning, we can train these parameters using physics-based model. In this example, we have infinite slope model, right? We can train what this two-layer ANN model to predict our shallow slope equation. So that's the physics. We train this with our physics model. And then they got fine-tuned after learning all this additional landslide database. So this is I think this will help us navigate the debris flow database a lot better. So this is the results. So the figure on the left is without physics-guided initiation. So in this case, we use the ANN model with only 50 debris flow locations as a training data set. So this is a classic problem that is for machine learning that is out of sample location. Because in this area that is circled by this red, by yellow circles, essentially that area it contains low data. So machine learning has not seen any data in this. So this is out of sample location. You couldn't figure out what is happening in this region. So you have this false negative region. In fact, this region is completely flat. There shouldn't be any debris flow hazard. Now with the physics-guided initiation, we still use the 59 debris flow data points. We can better steer the machine learning model towards better physics. So the model figured out this is a flat area. There is no landslide. So we completely eliminated these false positives. The next one is a little bit more complex, but overall it's still manageable. That is physics-guided loss function. Now, loss function is another jargon that essentially it calculates the difference between model prediction and ground truth. So that's just the difference. Now, machine learning algorithms try to minimize this loss function. By minimizing the loss function, so we are able to match our model prediction with ground truth. So now we could add this physics-based loss term. So we can just say we're going to force this machine learning to obey certain physics law. So you can construct this physics loss term any way you want mathematically. It can be very complex. But here we can just use one simple physics that, remember, in geotechnical engineering, as the factor of safety increases, the debris flow risk definitely should decrease. You should follow this monotonic relationship, right? That's the right physics. We can calculate the factor of safety based on infinite slope model, and as the factor of safety increases, the risk should decrease. So anytime the model prediction violates this physics, we're going to penalize it with the loss term. So by minimizing the physics loss term, our machine learning model output will be much more consistent in physics. So this is the result. The left is without the physics guided loss. In the circle, you can see that the area, you have several predictions with a very high calculated factor of safety, 6, 7, 8. You should have a landslide debris flow risk 0 because the factor of safety is so high. Now with the physics guided loss, we have a much more monotonic relationship. So we are steering the machine learning towards better physics consistency. So I just want to make some simple conclusions that in this study, we show that both physics-based shallow landslide model and the machine learning models trained with our inventory, we can predict the debris flow risk in the area pretty well. And also physics-guided machine learning model can improve machine learning model performance under limited data condition, improve physics consistency, and make machine learning models more generalizable. So I would like to acknowledge this research is supported by a Google project and also NSF and the Penn State's University Transportation Center. I'm currently organizing a couple of workshops to bring machine learning people and geotechnical engineers together to discuss how do we incorporate the physics, landslide physics, into machine learning model to map our landslide and predict the landslide better. The first workshop occurred in May of this year at Penn State. Next workshop will be next year in Alaska. Our goal is to map and predict permafrost-induced mass movement in the Arctic and the subarctic region. That's our by incorporating permafrost-specific physics. Thank you very much.
Thank you, Professor Chu. Questions? Yeah, sir, here.
Very interesting work. Just accidentally, or coincidentally, we were doing some similar work in terms of predicting the deterioration of asphalt pavement using penalty function, penalty loss function, and all that. So it's very interesting. This is commenting into different subdisciplines. One question is slide 12, where you initiate, initial value. Could you elaborate how, because that's the part I didn't quite get.
So you want to know how we use physics guided machine learning to initiate this?
Right.
So you can, as you can see that we can use the physics guided machine learning to make the model predict this equation. So you use this physics model to generate a lot of data, and we train the the machine learning model to predict exactly that equation, and that is your starting point. And then you use data, additional debris flow data to fine tune it. So that's sort of transfer learning in machine learning.
So in that case, that equation is always simplified scenario, but
That's
it's
right.
a good starting point.
That's right. That's right.
I think the last of the 3 sites going to that, one the venue, yeah, this one. So I say without the physical guided loss, with the physical, it's all, to me, it's a little 0.939, 0.9336.
Yeah. So yeah, are you saying that the AUC score decreased if we incorporate the physics?
So I think it's a very little difference. That's what's the meaning of that,
No.
See, that is very sensitive to that.
No, actually, the fact that they are the same actually is good news. That means you look at these two models, right? The model on the right with the physics guided loss, you are obeying this monotonic relationship, right? So you have a better physics consistency. Now we are not, even though we have a better physics consistency, we are not sacrificing our model performance because our AUC score only decreased by 0.003. So that is actually a good news for us.
Yeah, one question back here that we have follow up on.
Okay, well, I have a question about Cohesion. Use the USGS band and put it in the form. You know that the USGS band just gives you sort of this. Yes. So this is with performance analysis. Performance and results. Also, at the same time, you're school. Kind of have to get a third layer at the bottom. So it's interesting.
You're absolutely correct. So the problem here is, remember, we discussed this equation. So this is related to the sliding layer thickness, right? We said that actually in this study area, the thickest, this is based on post-disaster survey, the thickest sliding layer thickness is only 0.4 meter. So that is pretty shallow, and so that's why we use the USGS as the data. That's right. This is the debris flow. If you look at this picture, the debris flow is, we can use shallow landslide.
So how did you predict swim orbits? Because I noticed that you said that same thing. How did that be at the Cohesion?
The open land map so has a sand content, the clay content, and the silt content. The three combined will give you 100%. So we use sand content and clay content using an empirical equation came up with Carlos Santamarina, the student in 2017. So this figure shows this empirical relationship.
So, but for some cells, sometimes the particles change. This should be forgiven. Similarly, granular material is very fine. In such instances, you do not specify the kind of particles that
So what you are saying is a much deeper question. That is, for example, I will answer your question this way. I think you will agree that remember we only studied this Boulder County area, right? So it turns out that I cheated a little bit because in this front range it covers 4 ecoregions. So these 4 ecoregions, they have a drastic different geology. Now, if you don't use the physics-guided machine learning, you just use machine learning, then the model you learn from one ecoregion, you're going to have a hard time applying to another ecoregion. But our results show that if you incorporate the physics, then your model you come up with for one ecoregion can be much more transferable to the other ecoregion. But due to the time constraints, I did not present that. So you're absolutely right.
Okay, I think we should wrap up there. One last question on mine, it's a very quick one. Regarding the physics-guided loss function, is the penalty term a constant or is it actually a function itself?
The penalty term is a function, so you can construct the function in whichever way you want. So this one, we're just using a simple monotonic function, monotonic relationship. And you have this, for example, you can manipulate the lambda physics versus lambda data to see which one you want to respect more. So
excellent. Okay, well, thank you so much, Dr. Chu, and we'll
okay, thank you.